Quantum networking breakthrough. Researchers transmit quantum data on a live commercial fiber optic network. In a significant step toward a future quantum internet, a team of engineers from the University of Pennsylvania has successfully transmitted quantum information over a live commercial fiber optic network. This first-of-its-kind demonstration, detailed in the journal Science, proves that the fragile states required for quantum communication can coexist with standard internet traffic on existing infrastructure. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. The key to this achievement is a newly developed silicon chip that seamlessly integrates quantum signals with the classical data packets of the modern web. This integration suggests a more practical and scalable path for building quantum networks, potentially accelerating their development. The core challenge: preserving quantum fragility. Quantum networks rely on the principle of entanglement, where pairs of particles share a deeply linked state. Measuring one particle instantly affects its partner, regardless of the distance between them. This property could one day allow quantum computers to connect and combine their power, enabling unprecedented advances in fields like drug discovery and artificial intelligence. However, this quantum state is extremely fragile. Any attempt to measure or amplify it directly causes it to collapse into an ordinary classical state. This presents a fundamental roadblock for networking. Traditional networks constantly read data packets to route them to their destination, but this would destroy quantum information. The solution: a quantum train on classical tracks. The Penn team's innovation, dubbed the Q-chip, solves the routing problem by pairing quantum data with the classical signal. The system works like a railway. A pulse of classical light travels just ahead of the quantum signal. This header contains all the necessary routing information using standard Internet Protocol, IP, and can be read and measured without issue. The quantum information follows closely behind, its delicate state protected within the sealed container of the optical fiber. Because the classical signal leads the way, network switches can read its destination address and configure themselves to guide the entire train, quantum cargo and all, to the correct location without ever touching the fragile quantum data, explains Yi-Chi Tsong, the study's first author. Adapting to real-world conditions. A major hurdle for quantum technology is operating outside the controlled environment of a laboratory. Commercial fiber optic cables are subject to temperature shifts, vibrations, and other disturbances that can scramble a quantum signal. The research team developed a clever error correction technique that leverages the paired signals. Since both the classical header and the quantum data travel through the same noisy environment, they are affected similarly. By measuring the distortions to the classical signal, which is allowed, the system can infer and apply the necessary corrections to the quantum signal without ever measuring it directly. This approach allowed the system to maintain a quantum state fidelity above 97% on Verizon's campus network in Philadelphia, demonstrating remarkable resilience to real-world interference. Implications and future directions. While this breakthrough is a critical proof of concept, building a global quantum internet still faces significant challenges. The most prominent is signal loss over long distances. Unlike classical signals, quantum signals cannot be amplified with standard repeaters without destroying their quantum properties. Solving this will require the development of quantum repeaters, a technology still in its infancy. Nevertheless, this research provides a crucial piece of the puzzle. It demonstrates that the core networking protocols of the modern Internet can be adapted for quantum data, suggesting that future quantum networks could be overlaid onto much of today's existing fiber optic infrastructure. We've shown that a quantum network can speak the same language as the classical Internet. This compatibility is essential for scaling up from our current two-node experiment to a larger metropolitan-scale network and eventually beyond. The work evokes comparisons to the early days of the Internet, when connecting isolated networks unlocked transformative potential that was difficult to foresee. This demonstration marks a similar milestone, bringing a powerful new form of communication closer to reality.